background because I don't think I have like a straight background into audio music, so I wanted to share that as well. So in now it's really, you know, a long time ago, 2011, I got a bachelor degree in Politecnico di Torino in computer science engineering. And then I got a master degree in computer science engineering from Politecnico di Torino, but that was a double degree together with the Universitat Politecnica di Catalunya, where I got a master in innovation and research. And that didn't want to be a double degree, but it happened to be because here in Europe, we have this project where you can apply, and if you get selected, you can have a fellowship and go abroad and study abroad in Europe for a period that goes between 6 months and 1 year. And in Italy, the master degree is 2 years, while in Spain, the master degree is 1 year. So I had the full master there because I studied there in Barcelona for 1 year. But at that time, my interest was like in space. So my first final project, it was related to a data optimization layer, like of an European Space Agency mission. And that was not involving music or audio at all. And then I kind of like fell in love with the city, with Barcelona. So I decided to stay there. And here you can see, like, I started working as a software developer. I worked for a while in HP. And also then I joined like a small center of, it's not that small actually, like a research center of bioengineering of Catalonia. But then, like, you know, Barcelona is really active city, especially like in terms of music, contemporary music, electronic, ambient. So I start to get involved into that. And also I realized if I want to work all of my life, it needed to be something cool. And then I start looking around and I start wondering how I could merge like computer science and music, if there was a way to do that. And I found this master. There are also like other kind of master, but I was living in Barcelona already. And this is one of the best master you have like in sound and music computing from Universitat Pompeu Fabra, which is offered from the music technology group. And I applied for that, luckily I got accepted, and that was a game changer in my life. But for my final project was on sound event detection, actually with the submission of one of the challenge that I'm gonna talk about next. And at the end of the master, I wasn't sure if I wanted to get fully involved in research or not yet. So I worked for a year and a half at IRIA, which is the National Institute of Research in France. And the focus was still on sound event detection. And I got involved with the topic. I really like it. And I was at the end of the project, I was like, okay, now I'm sure I want to do a PhD. And then I applied for a PhD in Politecnico di Milano, where I'm currently at my first year at I'm in the image and sound processing lab. And yeah, I'm currently the topic that I'm working on are sound event detection. I'm also working on space-time audio processing, but as Iran said before, I kind of like want to get back to work with music information retrieval task. And I'm mainly interested in generative music and loop generation, synth loop generation, drum loop generation. And this is why I'm here at this workshop, mainly because I'm really interested into music. So I kind of wanted to make it a bit interactive. So I don't know if you have questions so far. It's a lot of logos, but it's because I'm old, not because like.
I guess when you were in MTG, who were you interacting with?
So the MTG, like the cool things, I don't know if at Karma is the same, but we were like a small class of people. We were just like 20 students, and you kind of interact with all the PhD students that are there. My supervisor was Andres Perez and Daniela Arteaga. I don't know if you know them. And I was mainly interacting with Frederick Front, and Xavier, of course, it's kind of like, it's present, is always present.
Yeah, I know those folks. Well, I just wanted to connect the dots. MTG is a very important center in the world. And one of the founders, one of the main professors there is Javier Serra, who got his doctoral degree at Karma as well. So did you get to interact with Javier, Sarah?
Yeah. I remember going to him when I applied to the master because I really want to get accepted. I really wanted, to get involved in sound and music computing. And I remember going to him even before getting accepted. And I asked him like a meeting because I wanted to explain the reason why I wanted to go into the master. And yeah, it's really super nice person, super present. Yeah.
Yeah. Cool. Any other questions about her background? On Zoom? Don't be shy. Okay, well, we can continue.
We can continue. Then I don't know, now I'm gonna get into like sound event detection. If any of you ever heard about the DCASE challenge, but I don't think so. So the DCASE challenge,
anyone knows about, has anyone ever participated on this challenge? Or heard about it? Let me see a raise of hands. So a couple people in the classroom are saying they have heard. And then what about on Zoom? Okay, I would need to go and see who's raising their hand.
Okay.
Because let's see. No raised hands. Okay.
Okay.
You're gonna tell us all.
Yeah. So it's basically a challenge which is running every year. It's the topic is on detection and classification of acoustic scene and events, and this is where DCASE is coming from. And it's running every year from middle of March until this year was a bit before the usual deadline, but it used to be July, mid of July. And you have different tasks. This year was the edition where you have we had the highest number of tasks, and all of them are focused on a particular, let's say like limitation of systems or some particular topic you can have on the DCASE like topic at large, let's say the machine listening topic, I would say. And what happened is that at the beginning of March or middle of March, when the challenge starts, the different teams that organize the challenge release the task description, of course, and then the development data set and the baseline system. And usually the baseline system is not really complex system, and it is beatable because the goal of the organizer is not to give a baseline that people cannot beat, but is to trying to get it attractive for people to submit a new solution or different solution, and to see where the state of the art systems go year by year. And there 15 days before the closing of the challenge, we also released the evaluation data set, which, as Iran was saying, I think a couple of days ago, like we just released the data, but we do not release the labels of the data. And then what participants do, they run the system on this evaluation data set, and then they submit the output of the system. We evaluate them and we give back the results. And for example, like for each task, I can take this one, you have the description, you have, if we go to subtask number 4, you have all the description, all the, different kind of like rules that you need to follow to submit your system and the results and all the information. And then after the challenge, that you need to submit your output, but also the technical report that can easily become a paper. And there is a workshop that is organized at the middle of September. November is also changed a bit every year. This year is going to be at Tampere. And you can not only submit the description of the system you propose for the challenge, but any study or research related to the DCASE. And if you get accepted, he's going under a blind peer review process. Then you are invited to present your work or your study at the workshop. And I don't know if there are questions so far.
I'll just say that, the word challenge makes it seem, oh, this has to be so complicated, right? Like I'm not ready for this. But this is one of the most welcoming communities you can encounter right now in the field of machine learning. And you know, the process to get a paper accepted or to get your system published, it's not even like you have to be the best one. They value all sorts of ideas, all sorts of contributions. And, you know, a lot of people go to this workshop, even if your idea is not related to the challenges. Maybe you have an idea about how to do a task in a way that, you know, nobody else has thought about, and you even think that, oh, that's so out there, that's maybe it's not gonna work. But they value even, you know, those ideas that maybe too off, but with the idea of getting feedback and reinforcing and getting constructive reinforcement of principles to make new systems and new problems and new solutions. So I just wanted to say that it's one of the, if you haven't looked into this particular venue, you should look into it, because it's really, really nice, and it's a very welcoming community and opportunity.
Yeah, I agree. And it's also what exactly what you say, like it's not only about beating the baseline, but it's kind of like improving the system and the quality of the system, and raise awareness about problems that can be, for example, like biases, or we will see about like energy consumption. And it's the baseline are usually easy systems, or they're not too complicated. So it's also a nice way to start if you're interested in this topic, to, you know, to start with the systems that are used, or also to have which kind of data we are using. And also I wanted to add that there are different challenges for different topics. I think there is also like AI music contest, or there are challenges related to music information retrieval tasks. So it's a nice way to start to work on some topic. And yeah, so we are organizing the task number 4, the challenge task number 4, which is sound event detection in domestic environments. In domestic environments is mainly because we want to give an application to the sound event detection, and to focus on you know, on a real world application. So the different, I would say it afterwards, but the goal of the task is to evaluate system for detection of sound events using real data with different type of annotation and corresponding labels that are available for training. So what do I mean by sound event detection system? It's basically a system where you give an audio as input, and the system, the goal of the system is to be able to detect the different events that are present in the clip. So for example, in this case, we have dishes, speech, vacuum cleaner, but also to be able to exactly detect the onset and the offset. So where the events is starting in the clip and where it is it's over, like when it's finishing. And one of the challenges is that the events can be present at the same time, and more than one event can be, you know, present also like in the clip, of course, but at the same time. Like here, for example, we see there is an overlap between dishes and speech. And what I mean by having different type of data is that one of the let's say like the goal is not of this particular task. It's not really about having system for sound event detection, but is to train them with an heterogeneous data set. So what I mean by that, I mean that we have 3 different type of data that we give to the system of training. We have a huge subset of unlabeled data for which we have no information about onset, offset, but not even the events that are present in the clip. So we just give the audio clip to the network. Then we have a subset of weak data for which we only know the different class events that are present in the clip, but we don't know where they are happening. So for example, in this case, for this audio clip, we just know that there is speech, dishes, and vacuum cleaner, but we don't know where in the audio clip. And then the last subset is strongly labeled data, that here they are referred as synthetic data, for which we have all the different, you know, the complete label, onset, offset, and classes events. And one important point in this data set is that for weak and unlabeled data, we are using recorded data, audio clips. So we are using real data coming from real recording, But the strong label data, at least until 2021, and we will see how this data set improved during the years, the strong label data set was synthetic, was automatically generated or synthetically generated. But then we are testing the system on recorded data, because this is our, the application, the goal is to test the system on real data. So here is how our data set evolved during the years, because as we said before, the goal of the challenge itself is not to, it's try to be attractive to people, but also every year to find limitation of the system, of the data sets, try to improve the quality and the challenge itself. So the challenge was launched in 2018 by Nicolas Troupeau and Romain Sarissal. In 2018, there was they released the challenge with the DCASE dataset, but the dataset was formed just by weak label and the label data. There was not synthetic part in it. In 2019, they used DCASE, which is a framework, is a library that you can use to synthetically generate audio clip. They added a synthetic strongly labeled data part to the dataset, and this is how how I described the dataset before. And then in 2020, which is also the year that I got involved in the organization of the challenge, we added recorded strongly labeled data. So we also added a subset that was coming from AudioSet, which is maybe the biggest data set we have nowadays. It was released by Google, containing audio files where you can use for training your system. And in 2020, they released the labels for part of it. So we are using a particular part of this audio set to train our system as well. So to have like a part of recorded data. And then in 2021, we also added non-target events to the synthetic part of the data set. And why did we do that? We did it because we realized that our synthetic strong label data set was only considering the target sounds. So the sounds that you want to detect. But in real world, in real audio clip, you also have a quantity of non-target events, of other events that need to be considered, that the system should be aware of. And we added these non-target events to the synthetic part of the dataset to be able, to decrease what is called domain mismatch between different kind of like datasets. There are any questions so far?
Any questions, folks? So when you say out of domain, you're referring to just filtering out things that you don't care about.
Yes, but we had them. We had it like target events that we don't care about.
And so these are recordings that are recorded in specific rooms, right? So I'm assuming that the test set is a completely new room?
Yes, yes. The test sets are audio that the system never have seen, but they're not recorded in rooms. Like we are basically using YouTube video and Vimeo video, and we are extracting like 10 audio clips from there. So they can be from everywhere, yeah.
So it is still kind of synthetic. It is still the scaper style of putting together, or there's one part I don't understand about your definition of real sounds. I understand you're getting them from YouTube, right?
Mm-hmm. Yes.
Is it like strong annotation of the event start and end, or is it just like, oh, in this YouTube video somewhere there's a vacuum cleaner, for example?
Mm-hmm. Yeah, so the recorded strongly labeled data that has been added at training, it's coming from AudioSet. Yeah. And they release the label for part of that. While for the non-target events, we added those only to the synthetic strong labeled dataset. And for that, it's kind of like, so Scaper, we're using different kind of data sets to build the recorded, to synthesize the recorded, not the recorded, oh, sorry, to synthesize the audio clip. So all the different events and background noise, it's real, but the audio clip has been automated, it's been synthetically generated. I don't know if this answers your question.
Yeah, that answers. Good, thank you. Are there other questions? If you have a question on Zoom, go ahead. Anyone? No? Okay, let's keep going. Thank you.
Okay. Okay, then we also like improved, at least we try, like, we changed like metrics during the years, because in 2018, the challenge was released and all the submissions were evaluated using the HEF score that we talked about it a couple of days ago, I think. But in 2020, this paper was released at HiCaps, and this new metric, the PSDS, which I'm going to talk in a while, has been introduced, and we also introduce it as evaluation metrics in our challenge, and I will tell you like the reason why in a while. But then in 2021, we also wanted to raise awareness about the energy consumption about deep learning systems. So we also introduced this new metric, which is the energy weight PSDS metric, which we are not considering for ranking the system, but from this year, we force participants to submit it. Like, it's mandatory now to submit the energy consumption of the system. But between 2021 and 2022, we also realized that this is not a strong metric and is not an objective metric. So we also ask participants from this year to submit the number of operations that the neural network is doing to have like a more objective metric. So also, like, as you can see, like the data set and the metric keep changing over the years because of like thanks to the challenge, and then thanks to the community and the feedback we also receive, and also to the different analyses we do on the system. So the metric, the PSDS, is called Polyphonic Sound Detection Score, and is more robust in subjectivity in terms of labeling, and also it allows you to focus on specific application scenarios. The metric itself is not really easy to digest, so I will not go into detail, but it's just to give you an idea. You have different parameters that you can set, and you can decide if you want your system to be you can define different scenarios. And for example, for our challenge, we define two of them. The first one is to ask the system to react fast upon an event detection. So we really want to be sure that the system is able to detect the event at the right onset. And for the second scenario, we ask the system to avoid confusion between classes. So we prioritize the classification task, but we are not really strict on term of like in terms of timing. So it's the reaction time can be less crucial. So, and you can define your scenario, like you can set your parameters, and you can decide if you want to be really strict in terms of timing, really strict in terms of classification, if you want to have like a balance between them. So we define those two different scenarios. And participants can decide to submit the same system for both, or they also can submit different systems to the different for the different scenario, for the different metric. And then we are taking the best of the two metrics to define the ranking score. So I don't know if there are questions so far. Otherwise, I will go a bit deeper into the different research.
In your evaluation of the models, these two metrics are weighted equally, like when you consider,
yes.
Yeah. So
yeah.
But I guess you do see that some teams perform better and on one than on the other.
Yes.
Okay.
Yeah.
Yeah. So the decision to make them weigh equally, I guess, yeah, sure, both are important, but are there opinions? Because, you know, this is 2020, right? So that's a few time has passed. Are there opinions nowadays about which one should be more important than the other, or are the community still like, no, people need to get both?
Yeah, we're still like, until this year, we still consider both, and we consider both equally, but now it's clear that the PSDS1, which is like the time detection, where we're strict in terms of timing, is the most difficult one compared to the classification. In fact, even we will see it in the results, but in terms of performance, also this year, for example, all the different systems were able to beat the baseline in terms of PSDS2, but there are still systems that cannot for the PSDS1. And maybe like this means that the same team is able to beat the PSDS2, but not the PSDS1. And I think we are going in the direction where we are focusing on this scenario in the future. Yeah.
We have a question here from.
Mm-hmm.
Is the task of PSDS1 just more difficult, or do you think you're seeing just like, even if it's not like explicit, like more of a priority on scenario 2 that just kind of plays out naturally?
Mm-hmm. Yeah, it's more difficult compared to the second scenario, because the second scenario, you can think about something that is getting closer to audio tagging, where you have an audio clip and you need to define which class is inside your audio, but you don't care about where they are. So we are kind of like more flexible. If the event is evaluated, it's recognized like, let's say 22,200 milliseconds after it actually happened. While for the PSDS1, we want to be strict in the onset, let's say. So this is more difficult because the system needs to be really precise for all the different events that you have.
And I have a kind of a weird question along those lines, so the PSDS is actually, it's in units of milliseconds, right?
It's not like in milliseconds. So the PSDS is kind of like considering the false positive rate, the false negative rate, but it's also considering the cross trigger events. So it's a mix of them, and you can set the different parameters, but it's considering the timing.
So my question is, so it's a number that goes, I guess, between 0 and 1, right? Where
yes,
that it's doing it perfectly. Is it practically possible to go above 1 if the system starts not reacting but anticipating? Like, what happens if here the keyword is react, right? And I'm sorry to pick on this, but my PhD dissertation has 2 chapters on anticipation. So I'm always thinking like, oh, if something can react, why can't it anticipate? I guess the question is more like, do you see that some of these systems like start anticipating, like given the priors of an acoustic scene, do they like not just react, but actually, oh, the next sound that is going to show up is going to be the next step is going to be the dishwasher, because people were just like putting a bunch of dishes in the sounds that happen in this scene. Is that going on or no?
Yeah, that we should do an analysis on that and try to understand if this is what happened. Like that's a good point. Like I don't have an answer right now, but that can be interesting to investigate. Yeah.
Thank you.
Okay. Then I will just present some results on one study that we did on 2021, where we studied the impact of non-target events in synthetic soundscapes. So that was the year where we added those non-target events, which are events that we know they are in the audio clip, but we don't want to detect those events. And we wonder how non-target events influence the system at training time, if we can find a target to non-target signal to noise ratio condition that could match better the recording soundscapes, And does the system get acoustically confused by similarity in sound between the different events? So for the first question, how non-target events influence the system and training time, what we did was to include and to not include non-target events at training and validation. And what we have seen is that for these, all those studies were done on the baseline. So we have seen that the baseline got the best performance where non-target events were included at training and at validation. And also, like, I need to point it out that this was evaluating the system on real recorded data, because we will see afterwards some results on synthetic soundscapes. So, and also, here's the first difference between the two scenarios. For the PSDS2, we can see that the improvement is higher compared to the one that we got for the PSDS1. So this is already like a difference between the two scenarios, and we can see also how the performance are different for the different metric. So here, the baseline is really, you know, it's kind of like low, the results, but here we are able to reach almost 60%. And then we wonder if we can find a target to non-target signal to noise condition that could match the recorded soundscapes, because at training we have for the synthetic part, we are mainly working with, for the strong label part, we are mainly working with the synthetic. Those are the data that we are able to control. And we decrease the dB, which is kind of like the target to non-target signal to noise ratio. It's kind of like increasing or decreasing the loudness of those events. And we decrease the loudness of non-target events compared to the target one by 10 dB and by 15 dB. We also did it for 5 dB, but the most interesting results were for 10 dB and 20 dBs, where we see that if we decrease the non-target events at training, but we keep the non-target events as they are in the validation set, we are able to have, like, it's the case where the baseline is giving the best performance. And anyway, the performance are not really different between them. So it's kind of like, it's really gaining a point, but we probably, like, one intuition was that maybe this is the situation where where sounds get close to the recording sounds, to the recorded soundscapes. And then we did a last experiment to try to understand if the system gets acoustically confused by similarity in sounds. And what those columns are saying, here are the classes that we are trying to detect, that the system should be able to detect. And here is the number of events that we have in the evaluation set. And for column A and for column C, we did not include the non-target events at training, while for column B, or for column, this one is the baseline, we did include them at training. And what can we see is that you get confused for, I didn't specify, I think, like in this evaluation dataset, we only have non-target events. So for this evaluation dataset, we are not considering target events, only non-target events. And we were curious to see if there was some false positive and which kind of false positive was more, was outputting more the system. And of course, there are, for example, events like speech where we have a higher distribution in terms of events. But we have seen that, for example, for DCASE, the difference, if we include or do not include non-target events, it's really big. Like when we don't include them, it's outputting a lot of false alarms. So probably percussive sound, or there are some sound similarity that non-target events help to reduce. And in another study for another paper, we also have seen that the system tend to output false positive mainly for short events compared to long events. And it also will make sense to investigate it more. So I don't know if you have questions related to the first, like this result or the previous one.
I mean, this is super interesting, but if I'm understanding correctly, you literally show during test time tracks where there's only non-target stuff, right?
Exactly, yeah.
And you're just getting the actual hits, right? Like you're But did you look at the, I mean, I don't know if you were interested in this kind of thing, but did you consider also looking at the embedding space of these things to see if which ones the model just like really maybe clusters them all together because they are just non-target events versus which ones, even if they don't become hits, the model is just like really thinking about them as, like, you know, not like, I don't care about that, but more like I'm confused. Did you look at any like that, like the embedding space plots or things like that?
Yes, kind of like I started, I actually submitted like a DCASE, but I need to work more on that. What I did was try to consider them at training as well, but not as non-target events, just like consider them at training as an additional class. And but then evaluating the system only on the target events to try to understand like if giving them has like, for example, like all those events are garbage or like trash classes, so you don't need to consider them because then we're not considering evaluation or anyway force the system to, you know, to put all the different events there. But it kind of like showed that it improves a lot when all the different classes are considered. It confuses the system even more. But when you include all of them into the trash class, it might help the system a bit. Now, like the next step will exactly be what I want to do is like to make clusters to understand the similarity and then try to train the system considering the different cluster. Because for example, we have some non-target events that might confuse the system. For example, we have like liquid and we have water here. So I don't know if this can be confusing for the system because the sounds should be similar. So this is like one of ongoing research. Yeah. And looking at the embedding space can be interesting.
Very interesting. This is so Francesca.
Thank you. And yeah, I wanted to share these results because one of the key points is that it's true, we should go to real data, but for us having synthetic data or generate synthetic soundscape give us the possibility to analyze the system a bit because you can control those events. And yeah, if there are no other questions, I will go to the second paper that I wanted to talk about a bit, and it's a benchmark of the state of the art that we have for the challenge that has been evaluated on synthetic soundscapes. And this slide can be a bit confusing, but yeah, I will say a few words before going to that. So as I said before, participants can submit different systems for the different scenario, and we are considering the best for each scenario to give the final rank. And here, when we did this study, we focused on the top 10 ranked system, and out of them, we took 3 systems that were using the same submission and 3 teams that were considering 2 different submissions. So for example, here we can see that this team used different system for PSDS1 and PSDS2. In fact, like here is the best performance for PSDS1, but the best performance for PSDS2 is this one. While, for example, like the second team used the base system. So you will see the same for performance for both metrics. And we analyzed the system. This time we evaluated all of them using a synthetic evaluation set where we were able to move like we were able to move the events in time. And here what we did is also to study the impact of target to non-target signal to noise ratio for non-events and event targets. And here in those 2 plots, in green are the system that use different submissions, while in red are systems that use the same submission. And what is interesting to see is that, of course, those are synthetic evaluation data sets. So what we are seeing is that the TNT SNR0 is where the non-target events are like laudable as we define. But in this case, it's kind of like you basically don't have non-target events in the evaluation scenario. And what happened is that the drop for the system that fine-tune the submission, it's smaller than the drop that you have for systems that did not fine-tune the submission for the different scenario. And this happened as well. This is a bit strange because we consider the system submitted for the PSDS1, but for the second scenario. And we see that the drop is more or less the same for all. And we did it also for the PSDS2, and you can see this difference even more than before, because, for example, it's true that the green system are not performing as good as the red system in cases where you have where you don't have non-target events at evaluation, but the drop that you have in terms of performance is way smaller than the red one. So it is important if you to consider the application and to consider the scenario that you are working for and that why you are developing your system, because it's important to to build the system considering the application that we are doing. And then here, what we did instead was try to study the system mainly for the first scenario. So we took the best submission for the PSDS1, where we are strict in time, and we moved the onset of the different events that we have. So in this case, we moved the onset of the events, some of the events, to be at the beginning of the audio clip. Here, we put some of them in the middle, and here we put them at the end of the audio clip, the onset. And we also, in this case, we see that if the system has been fine-tuned and has, the application that you are developing the system for in mind, let's say, the drop is really like the system is way more stable than system were not fine-tuned for that. And we also should look into that because it happened. We did a similar analysis in 2021 and we got the same results. So when you put the onset at the end of the clip, like it's dropping down the performance for most of the system.
Like the system saying like, oh, I'm so done with this.
Yeah, it's like, I don't want to wait the end of the clip. Yeah, exactly. And here's just also, I want to say, like, I try to, to put like the most interesting plot or results. Of course, it's like you have a bit more in the papers. For example, also this is where we studied the false alarm in terms of timing for the different systems. And we are seeing that they are outputting false alarm mainly for short events compared to long events. And yeah. And then the last thing that I wanted to introduce, I don't have any results for that to show, but it was just to take this as an occasion to raise awareness about the energy consumption of those deep learning systems. And we try to do that introducing this metric where we are weighting the PSDS for the energy that is being consumed by the different submission normalized by the energy consumed by the baseline. We are not taking this metric into account when we are ranking the system because we are aware that it's not an objective metric. And we are currently working on that. There's gonna be, here is where we introduce the metric. So it's the reference is here. I'm together with Roman and Constance. She's a PhD student from IRCAM. We are gonna have a tutorial at the DCASE workshop this year that is going to be exactly on the different metrics that we can use to measure the environmental impact of the system, to raise awareness, to have a case. There is gonna be a case study of the system of this year at the DCASE, especially like focus on energy consumption. And last year, there was also this paper that has been presented at HiCast, sorry, it was this year, on the consumption versus performance of the baseline that we're using for our task. And this paper present kind of like an ablation study on the baseline where we actually dated, change different parameters and different hyperparameters of the network to try to understand what's impacting the most the consumption of the network. So yeah, I just want to take this as an occasion. And yeah, I think this is what I have for today. Thank you so much.